Hello, all AP Calculus AAB students. Mr. Record here, getting ready to talk a little bit about this concept in our section 3.7, optimization. If you're a student of mine, you're able to use your notes page to go ahead and follow along with this video. If you happen to be a student outside of Avon High School and are watching the video, first of all, welcome. And I wanted to make sure that you were aware that you could gain access to this particular document that I'm using the link found below. I'm not going to read this first page. I know that you can all do that on your own, but this does do a pretty good job of kind of introducing what the fundamental principles are of optimization, the kinds of things that optimization will allow you to do. And you'll find out that it is one of the first really true, useful, real-world applications that you learn in AP Calculus. Anytime that you're looking to find things like the smallest volume, the least amount of time, the shortest distance, the cheapest price, things that businesses always are striving to do to keep afloat in this very competitive free market economy, optimization is typically something that they're going to be looking at on a daily basis. Now, our first example that we're going to do here, I'm going to try to get two examples in this particular video, doesn't have a whole heck of a lot to do with the real world. But I thought that this was a pretty easy problem to get introduced to optimization. It says in example 1, find two positive numbers that minimize the sum of twice the first number plus the second number if the product of the two numbers is 288. Now, the way that I always like to set my optimization problems up is by defining the variables. And it's pretty clear that you're looking for two things here, two positive numbers. So I have very little problem in saying, let's go ahead and let the first number, or the first positive number, equal x. It's a great place to start. And we look at into this a little bit further and we say, oh, well, you need a second number. Now I'm going to play dumb on this. I'm going to do the things that typically your algebra teacher would tell you not to do, and that's to let the second number be y. But we're going to be just fine doing that, just temporarily. Now, we look at the second piece of the problem, and it says that we want to minimize the sum of twice the first number plus the second number. The thing that I've underlined in red is a very critical part of this problem. A lot of times I will call that in my class the primary equation. That means he is the main equation that's sort of driving the solution to this problem. Now, I would go ahead and set up a true equation with that, which means I need to kind of make up another name for what I'm actually trying to minimize. And usually you just look for sort of the object of that subject. We're trying to minimize the sum. So I could just use the letter S. And it says I wanted to take, once again, twice the first number. Well, that would be 2 times x. And then I would plus the second number, or add the y. So that is my primary equation. That is the thing that I'm trying to minimize. And hopefully you've taken enough calculus up to this point that you realize that whenever you're trying to minimize or maximize something, you need to take its derivative and then go through the whole critical number process and find out where the signs change in a certain way of the derivative, etc. But there's a problem with that because we have an equation here that contains both x and y, and we don't want that. We want to take care of that situation. So that's where we introduce the secondary equation. It is quite common for many of these optimization problems that you see to be sort of dealing with the two variables, in this case x and y. And if that happens, you need to search down a secondary equation, which I tell my students is usually going to relate to some numerical value that's given in the problem. And if we read this little phrase, it says that the product of the two numbers is 288. Well, it's very clear that that means that you're taking your x times y and getting 288 out of that. Now, what does that say? Well, if x plus y is 288, we can use that. And since taking the derivative of this stuff in red was sort of problematic because of there being two variables. Let's fix that right now. You can choose to solve this equation for x or y. It really makes no difference. I think that it might be just a little easier to solve for y because we now have something that's all in terms of x. And what that allows you to do is just sort of use your good old-fashioned independent variable x throughout the rest of the problem. So I'm going to take this secondary equation and I'm going to move back over here to the primary equation, and I'm going to rewrite this s. I'm going to rewrite this s where the x stays as he is, but the y is going to take on a new name, particularly 288. Whoops, not over y. That's what I was trying to avoid. 288 over, let's see if we can erase here. That would be a wonderful thing. 288 over x. So you can see the substitution that we made there. Not a big fan of the way that this is written in terms of getting ready to take the derivative, so easy fix there. We can call this 288 over x, 288 times x to the negative 1. Now I think we are all set to take a derivative. So s prime, or s prime of x, if you want to be more specific, would be 2. And then the derivative of this guy will allow the negative to come out in front. We would have 288 times x to the negative 2 power, which could also be rewritten to save time as 288 over x squared. Now we're ready to find critical numbers, but I'm going to do one more thing first. I'm going to go ahead and get a common denominator among these two terms, which is very, very simple to do. I will multiply this 2 by x squared over x squared to produce this fraction, and then I'll just drop in the minus 288 on top because it already had the x squared in the denominator. All right, this is something that I like to do. Anytime that I have a fraction somewhere in a term of my derivative, I'll choose to go ahead and get the derivative written as a single fraction, because I always like to tell my students that finding critical numbers are a lot easier when you're looking at a derivative of this form. And that's where we happen to be now. It's critical number time. I'm going to slide over here, and we're going to recap the whole concept of critical numbers here. Critical numbers will occur in this case when the derivative s prime is equal to 0, or possibly when s prime is undefined. That's very important to consider. So when is s prime equal to 0? That would be when the numerator 2x squared minus 288 is equal to 0. So we'll go about solving this by adding 288 over and dividing by 2, and then taking the square root of both sides, which is going to bring about two answers, right? The square root of 144, when we solve like this, can give us the positive value of 12 or the negative value of 12. Now when we go over here to s prime, undefined, setting the denominator equal to 0 will just give us the answer of 0. Once again, anytime that you have a fraction and you're saying, when is this value all equal to 0? That's only going to be true if the top is 0. Fractions are only 0 if the numerator is 0. Fractions will then ultimately be undefined when the denominator is 0. Now it seems like we have tons and tons of critical numbers. Well, 3 to be exact. But that's not really the case, because if we remember, the original text of the problem stated that we want two positive numbers. If we look back at our critical numbers, we're going to say, wait a minute, 0, you're not positive. Negative 12, you're not positive. So really our only critical number is x equals 12, which is kind of a good thing, because if that's the only critical number that we have, then that's probably going to be the only value that we'll end up using, and consequently will be probably one of our answers. Well, I think that's going to be true, but I always suggest to my students that we want to check this. And to check this, we're simply going to use our quick little number line. A lot of different teachers do different things in this case. You can draw a giant chart to do a complete analysis of the intervals, the test, the sign conclusion. But for the purpose of an optimization question, We just want a really quick reassurance that we have our minimum or our maximum here. So what I do is I'll put the critical numbers all across the number line. In this case, we only have one. And then I'll figure out, what is the sign of S prime by trying various test values along the way. So let's pick something to the left of 12. Makes no difference what you pick. Just pick something that will be nice and convenient. 1 would work. And we could plug 1 into this S prime. Well, S prime of 1 obviously is going to give us 2 times 1 squared, which is 2, minus 288, which is negative 286, all divided by 1 squared, which is 1. I think it's pretty clear that we are negative. And then we could try something to the right of 12. Again, it doesn't make any difference. You could pick something that's kind of easy to work with. I'm going to choose 20. I think 20 is easy to take the square of. 2 times 20 squared, or 2 times 400, would be 800. And then by the time I take 800 minus 288, well, notice I'm kind of lazy. I don't want to take 800 minus 288, but I know that that's positive. And if I square the 20 down below, I know that I'm looking at a positive result. That's all I care about the sign. Since we do go from a negative derivative to a positive derivative, your graph of this function would go from decreasing to increasing. Now, I'm not going to spend a moment to graph this, but I would invite you to use a graphing calculator if you have one handy and actually take a sketch of not the S prime, but take a look at the sketch of the graph of the S and see if you truly do reach that minimum value when X is 12. It's a great way to sort of get another representation of this answer. So, what have we discovered? Well, we've discovered that X equal 12 truly is a minimum. So if we go back and think, well, what was the question asking again? It's been a while. Find 2 positive numbers that minimize the sum. Well, 12 is certainly one of those. Now we have to figure out what the Y value is. Best place to do that would be right back into this secondary equation. X times Y equal 288. So we just scroll down here. Make sure it does scroll down here. There we go. And we will use that secondary equation. And remember that 12 is now your X, trying to figure out what Y is. And okay, not the easiest kind of division that you're looking at here. I know that we did not use a calculator on this problem so far, so let's stick with that. So let's just take 288 divided by 12 the old-fashioned way. 12 goes into 28 twice. Do our subtraction. And I'm so thankful that this comes out even, because we were looking for probably 2 nice positive whole numbers. It didn't say that, but it's nice that we did get 2 positive whole numbers, 2 positive integers here. So we got our Y value to be 24. So I always like to answer a story problem with a sentence. So we would say the 2 positive numbers are 12 and 24. And that's the solution to example 1. Let's take a look at another example here that is a little bit more involved with the optimization process. It does have a link to geometry here. And this is the very typical, take a flat sheet of metal where you're going to cut square notches out of the corners and fold up the sides to make a box. All sorts of fun activities that teachers can do with this particular problem. I would like to teach, say, in an Algebra 1 class or even an Algebra 2 class, this same kind of problem. Although those students wouldn't know the calculus, they could play around with cutting out various notches around the sides of the box and folding up, and then we can find out, hey, which box will will allow you to house the most number of M&Ms or something cool like that. So anyway, the problem says you got this open top box that's to be made from a piece of metal 16 by 30 inches by cutting out squares of equal size from the corners and bending up the sides. What size squares should you cut out to create a box that has the largest volume? And then what would the maximum volume of that box be? All right, so you're really wanting to use a lot of space. You want this box to be big, but you just don't know how to fashion the corners so that that's going to happen. So, as we said before, we want to sort of identify the variables. Well, in this particular problem, I think it's kind of done for you. The picture's drawn, and you would use X for the dimensions of the squares of the four sides. I suppose if this problem did not have a picture, that would be your first step, and that would end up basically defining your variables. So we're really ready with the primary equation right off the bat here. And the primary equation deals with the idea of finding the greatest volume. So that would mean that we could use, say, a letter like V for volume. But what exactly is the volume formula that we're going to use? Well, if you would excuse my artistic ability here, but once these four sides are cut out and these sort of edges that I'm drawing in with dashed lines are used as folding lines, and then these four rectangular strips are just folded upward, kind of thinking of it as being straight out towards you, you would then have a box. And say a frontal view of this box might look something like this. There we have a box. All right, something along those lines. So the volume of a box, if you recall, or the volume of a rectangular prism, is just made up by multiplying the three dimensions, length, width, and height. We can call this dimension here the length, which sort of corresponds to the front here. Now you want to be real careful because we don't want to call this 30. 30 would be incorrect because that 30 would have been the entire length of the sheet, and that now changes because we have subtracted out a pair of x's. 2x's to be exact, so 30 minus 2x would be a great name for that dimension. And as the same vein, we could call the depth or width of the box 16 minus 2x. And then, of course, the height of the box would just take on the dimension x, because that x is the distance that you would sort of fold up that particular rectangular flap. So we have our three quantities, x, 30 minus 2x, does not matter which order you write them, and 16 minus 2x. This is your primary equation. And the good news, do we have a need for a secondary equation? Looking across, scanning this particular expression, we see only the variable x, which means we don't need the secondary. Now, I just chose to write this so that it was built in with only x variables. Other teachers might have done something a little differently where a primary or secondary equation could have been used. But sometimes I think it's just easier to write this straight up in terms of x. You are now ready to take the derivative. I don't quite like the form that this is in, so I think I might take the derivative a little bit differently. So we're going to go ahead and do some multiplication. 30 times 16, a little tricky there. You could think 3 times 6 is 48, but then you just need to add a 0. Let's see, the outside is going to give you negative 60x, the inside negative 32x. 60 and 32 make negative 92. Let's get this out of the way and get my pen back going. Negative 92x. And then we have, of course, a plus 4x squared there at the end. Now we have this x out in front that we need to multiply through. And I'm going to go ahead and rewrite the order so that it is descending. Just looks a little bit easier on the eyes. And I think we are now in a position to take our derivative. Finally, we get to do a little calculus here. So we'll take our derivative. V prime turns out to be 12x squared minus, what would this be, 184, I believe, x to the first, plus 480. All right, well, here we go. This is kind of an interesting polynomial that we're going to have to find critical numbers for. we're going to have to set the derivative equal to 0, remember, to find those critical numbers. Looking at this, I don't think we're going to have to worry about where the derivative is undefined since there are no fractional values. So we look at this a little bit and we think, oh goodness, how are we going to mess around with this? Does this thing factor? It certainly looks like it has the potential to factor, uh, but you probably want to find a common factor first, and it's unfortunate because these numbers just aren't real cooperative here. You can factor a 12 out of 480, but I don't think 12 will go into 184. You could factor a 6 out of the outer two, but I don't think, again, 6 will go into 184. So it seems like the only factor that they share is 2. So is that really going to help us? Well, we'll give it a shot. I want to kind of play along as you guys would be playing with this problem and thinking of different strategies. So if you do factor out a 2, 6x squared minus 92x plus 240, you probably realize, oh, I feel silly. I could have also factored out a 4. So that's fine. We'll go ahead and factor out a 4. So basically, you're factoring out a 2 again. 46x 120, but I don't think you're going to be able to factor anything else out. So you're going to have to kind of think about this just a little bit and think about, what are the kind of strategies that we can use to solve this. I'm going to go ahead and get my calculator up and ready to go. So now that I've got my calculator application up and going, just wanted to be able to verify the result of this. So, yep, I know this is kind of ugly. Once we've gone ahead and factored out the 4, we can largely ignore the fact that he is there because he's just going to divide over and become 0. And we'll figure out, well, can we go ahead and try to break this into 2 binomials? It does work. You just might have to find yourself being patient with this factoring technique. There's lots of videos out there that will show you how to do some of these complex factoring. But you think about 2 ways to write 3x squared, well, two terms that would multiply to make 3x squared, and you don't really have much of a choice. But boy, in the back end of this, two multipliers that make 120, you've got lots of options. 40 and 3, 3 and 40, 4 and 30, 30 and 4, 60 and 2, 2 and 60. You'll play around with those, and I'm going to jump right to just get right to the nitty-gritty. I'm going to use 10 and 12 here, and we'll find out that the signs must both be negative in order to produce a negative middle term and a positive last term. And you'll see that you do indeed get negative 10x in the middle, negative 36x on the outside for your negative 46x. So x would end up being 10/3 and 12. Now, I suppose if you did have calculator technology sitting around and you could do this, here's a couple of different versions of this answer. Let me show you. The cheap way to do this would be to use a CAS calculator like the TI Inspire CAS here, or say a TI-89, and you could just use the solve feature. But any graphing calculator will do a good job of sketching this parabola, 3x squared minus 46x plus 120, and you'll notice that the 2 places where the graph crosses the x-axis look to be about 3 1/3, and then over here at 12. And there are various ways on various calculators that you can actually pinpoint on these values. I'm not going to show you that. That's not really the purpose of this video. But all in all, truth be told, this problem could occur on a non-calculator type of assessment. It's just that you do have a pretty tricky factoring here. So once we got the 2 critical numbers, we look at this and think, well, we have 2 critical numbers. Well, is that really the case? You got to think about this a little bit, because one of these 2 numbers I think is going to be appropriate, but the other one will make very little sense. The one that won't make any sense is the 12. Because if you're talking about using 12 to cut off these squares, you cut 12 inches right there and another 12 inches right there. Well, that's a total of 24 inches. That's more than what you have to work with here on this side of 16. So that's not going to work. So we're going to eliminate him as a critical number, and we probably have our correct answer here of 10 thirds. But remember, we want to verify. We want to make sure that we do get a maximum volume. So we'll lay 10 thirds down on a number line, and we'll utilize the sign chart test here to find the sign of V prime. There is no reason to be cute. Let's pick some very basic, easy values to work with. I'll use 1 for my value of x, and I'll go into my V prime. I can go into any version of my V prime, but I'll tell you what, I happen to like this factored one real nicely. V prime of 1 would equal 3 times 1 minus 10 is -7, and then 1 minus 12 is -11. Definitely, I am positive right there. So, so I've got myself in a situation where I'm probably going to be looking at a max, hopefully. And then over here, I'm going to pick something safe like 4. That's to the right of 10 thirds. So V prime of 4 would end up being 3 times 4. 3 times 4 is 12. 12 minus 10 is 2. And then 4 plugged in for x over here. Subtract your 12, you get 8. It's pretty clear that that's negative. So we have our maximum. It occurs at 10 thirds. All we have to do now is make sure that we answer the question. And we are asked to figure out what size square should be cut out. Well, that pretty much takes care of itself. We could say we should cut out squares that are 10 thirds of an inch by 10 thirds of an inch. You could also just simply say 10 third inch squares. And then there's another question that asks you to find what is the maximum volume of that box. Well, that means you need to go back up to your volume equation, not your volume prime, but your volume equation, and plug in your 10 thirds into that. So the volume would be, and we might have to work that out just a little bit because it is kind of tricky given the fact that we have a fractional value. So I'm going to work down here just a bit, and I'll say 10 thirds volume equals 10 thirds multiplied by 30 minus 10 thirds times 2 is 20 thirds multiplied by 16 minus 2 times 10 thirds, which is 20 thirds. And then we can proceed to get common denominators. 30 minus 20 thirds would be 90 thirds minus 20 thirds. 16 with a common denominator of 3 would be 48 minus 20 all over 3. And then we have 10 thirds times 70 thirds times 28 thirds. And we have kind of a mess here on our hands. We have quite a bit of things here that we're going to have to multiply together. And let's see, we'd have 28 times 10. We could do that first of all. Or how about 28 times 7? How about we work that off to the side here? 28 times 7. Don't know that one. That's going to be 196. So since I've already multiplied the 28 and the 7, I just think I need to add a couple of zeros to make sure that I've taken care of the 10 and the 70. So I'd have 19600 as my numerator, and then 3 times 3 times 3 is 27. When that would be make for a great denominator. And as far as I know, that does not reduce. I could be wrong, and if I am, I feel bad. But you know what? It doesn't make any difference because on the AP Calculus exam, you don't need to reduce, but you do need to label. And we would want to label this with cubic inches, and that would be our maximum volume. Anyway, I hope you found these two videos very helpful, and good luck with your AP Calculus.